Dear all, a very good day. Now this is a continuation of previous lecture, and in this we are going to study about the electrical properties of MOSFET, its different regions of operation, and derivation in brief about the different current equations. Okay, now we can see here that this is a MOSFET structure with the source, drain, highly doped with n-type electrons. Now this is P substrate, our SiO2 and gate layer. Now this dotted line is showing the formation of channel. Obviously channel formation is very high on, is thicker on source side and thinner on drain side. The reason for channel being thin on the drain side is the biasing applied at the drain electrode, which results in a thicker depletion layer below the drain region, which results in tapered sort of channel. Now if the biasing is more and more increased, at the end the channel will be cut off from this. Okay, so we will see how this all works. So basically there are three regions of operation of a MOSFET: cutoff, linear and saturation. Okay, now the discussion which we are going to make is in relation with enhancement type MOSFET. It is more relevant to discuss with enhancement type MOSFET, where a channel does not exist at the starting, and slowly with the proper application of biasing voltages, channel is developed, and then different working which is happening are observed. Okay, so the first condition is cutoff. Okay, cutoff is a condition which happens at VGS, which is less than VT, that is the gate source voltage. Since source is at our ground potential, it is taken as the reference voltage. Okay, now if we apply a positive voltage at the gate, so difference between the gate and source potential is known as VGS. Now if VGS is less than a particular voltage VT, VT is the threshold voltage at which channel formation is completed. So if gate source voltage is less than the threshold voltage, okay, this means channel formation has not taken place. Since there is no channel between source and drain electrode, this means the flow of electrons between source and drain cannot take place. And since the source drain current cannot take place, this means that our channel is cut off, or device is cut off, and it cannot conduct any current. Then the second condition for our device which occurs is linear region. Okay, now condition for linear region is VDS is less than equal to VGS minus VT. Okay, now again source was at our zero potential and is taken as a reference, so difference between drain and source is known as VDS. Now if this drain source voltage is less than gate source voltage minus threshold voltage, then device is in linear region. Okay, and it operates linearly following the Ohm's law in most of the region. Okay, now in this region the channel has been completely formed as shown here by slight dotted lines. Now since this channel has been formed, current can flow between source and drain. Okay, and on proper drain voltage, current values can be increased. But the channel which has been formed is not a uniform channel, and it is a tapered channel, that is it is thicker on the source side and thinner on the drain side. Now this happens because source electrode is grounded, so not only a small depletion layer is formed below this. However, since drain potential is continuously being increased positively, and positive drain is connected to N type material, and body is also grounded, so P type is on zero potential. So this will result in this drain and body forming a reverse. In the reverse bias diode, the depletion region increases below the drain contact, and therefore this increase in depletion region causes the channel dimension to shrink. So this is all the depletion region here. Now the third region of operation is saturation region, in which drain source voltage is larger than our gate source voltage. Okay, and equation is VDS is greater than VGS minus VT. Now what this causes is, as drain source voltage further increase, the depletion layer will increase and ultimately cut off this channel from the drain terminal. At this time still the current flows in the device. Now why does the current flow in the device at this time? Because the voltage is so high that electrons gain enough kinetic energy to pass this small depletion layer between the channel and the drain terminal, and they enter the channel anyways, which causes a good flow of current. Okay, now here are the two curves, transfer curve and output curve for this MOSFET. We can see transfer curve is very straightforward between VG and ID. Okay, that is our input voltage, gate voltage is taken as an input voltage, and drain current is taken as an output voltage. So it is a transfer of characteristics between input gate and output gate voltage and output drain current. Now the other important characteristics is the output curve, which has been shown here, and this curve shows three regions of operation of the MOSFET. The first one is cutoff region, then there is linear region and saturation region. Now this output curve is between output voltage VD and output current ID. So we know if VD is very small, okay, and if VGS is very small, this is almost similar to or close to the x-axis, so our device will be in cutoff, that is no current will flow. But once VD is greater than VGS is greater than threshold voltage, so in linear current flows at it has been shown at different gate voltages. Okay, so this region here is the linear region divided by a line. Then anything after this is saturation region, where our VDS is greater than VGS minus VT, and hence the characteristics show a saturation and does not current flow does not increase. Now the other important thing is current equations in the linear region and saturation region. We know that in the linear region, in the cutoff region no current flows, so in cutoff region ID can be directly taken as 0 or negligible, which amounts for any minority current that is flowing. In the linear region, the equation for ID is equal to mu n C ox W by L VGS minus VT into VGS minus VDS whole square by 2. The same equation for the saturation region is ID is equal to mu n C ox W by 2L into VGS minus VT whole square. In the next lecture we are going to see how to derive these equations. Okay.